Dr. Dan with Optimal Optics here with Unit 5P, problems on the refraction at a plane surface. Question 1, what is the critical angle for light traveling from water to air? The formula is the sine of the critical angle equals n prime over n prime being the lower index, n being the higher index. Index of refraction of air is 1. The index of refraction of water is 4/3. So we have the sine is 0.75, and the angle is 48.6 degrees. How deep does a 12-foot swimming pool appear to be when looking straight down to the bottom? So when you have a medium surrounded by air, the apparent depth or the apparent thickness of the material equals the actual depth or thickness divided by the index of the material. So in this case, it's 12 feet divided by 4/3, and the swimming pool appears to be 9 feet deep. A ray is refracted from air into a medium whose index is 1.414. Find the angle of incidence. If the angle of incidence is 45 degrees, find the angle of refraction. So we're going to plug into Snell's law, n sine alpha equals n prime sine alpha prime. N is the index of the first material. For air, that's 1. Sine of alpha is the sine of 45 degrees. N prime is the index of the second material, 1.414, and alpha prime is what we're looking for. Now, if you recall your right isosceles triangles, the sine of 45 degrees is 1 over the square root of 2, which is 1 over 1.414. Now, to isolate the sine of alpha prime, we'll multiply both sides by 1 over 1.414. So the left side of the equation becomes 1/2. And 1/2, a sine of 1/2 corresponds to an angle of 30 degrees. Question 4, the height of a cylindrical cup is 4 inches and its diameter is 3 inches. A person looking over the rim can just see a point of the opposite side 2.25 inches below the rim. But when the cup is filled with water, looking in the same direction as before, he can just see the point of the base farthest from him. Find the index of refraction of water. Now, we know we're going to come up with an answer of 4/3, but this gives an example of one way scientists can determine the index of refraction of different materials. So here's our cup, and here's our ray from a point 2.25 inches below the rim without water. And now we'll make this ray blue. This is the ray from the base at the opposite side of the cup when the cup is filled with water. So after it's refracted, it goes along the same route that the ray took without water. We'll put an eyeball here, hopefully attached to the rest of the person. This is our 2.25 inch distance. The entire cup is 4 inches tall, and its diameter is 3 inches. So this is our angle of incidence, the angle between the incident ray and the normal. We'll extend the normal. And this is our angle of refraction, the angle between the refracted ray and the normal. So we can calculate the angle of incidence, alpha, with the formula the tangent of alpha equals 3 divided by 4. Opposite over adjacent. That equals 0.75, and the angle that corresponds to a tangent of 0.75 is 36.9 degrees. Now let's complete a triangle at the top of the cup. And we'll call this angle theta. And we can calculate angle theta because the adjacent side is 3 inches. So the tangent of theta equals 2.25 divided by 3, which happens to also equal 0.75. So theta is also equal to 36.9 degrees. Now let's calculate angle beta. Now you can see that alpha plus beta plus theta all have to add up to 90 degrees. So angle beta equals 90 minus 2 times 36.9. That equals 16.2 degrees. Now you can see angle alpha prime is the vertical angle to angle beta plus angle alpha. So alpha prime equals 16.2 plus 36.9. Alpha prime equals 53.1 degrees. That's the angle of refraction. So now we can plug into Snell's law. We're looking for n, the index of refraction of water. We know n prime, the index of air, is 1. So we'll be able to calculate our unknown variable n by plugging in what we do know. So n sine of alpha, which is 36.9. Equals n prime, which is 1, times the sine of alpha prime, which is the sine of 53.1. So n equals the sine of 53.1 divided by the sine of 36.9. And that equals 0.8 divided by 0.6, which equals 4/3. It works. Question 5, a fish is 8 feet below the surface of a pool of clear water, index 4/3. A woman shooting an arrow at a place where the fish appears to be aims her arrow at an angle of 45 degrees. Where will the arrow cross an imaginary vertical line that passes through the fish? So we'll draw our imaginary vertical line. And we'll draw our normal. And we'll draw the surface of the pool. We'll extend the normal. And we'll draw our ray at a 45-degree angle to the point on the imaginary line where the fish appears to be and where the arrow is pointing. And this is the ray of light from where the fish actually is in the lower left corner. And then after refraction, it bends away from the normal and goes along that same line corresponding to where the arrow is pointing. The total depth is 8 feet. That's my poor representation of a fish. We have our incident ray, and that's our refracted ray. That's our angle of incidence between the incident ray and the normal. That's our angle of refraction between the refracted ray and the normal, and we're given that that is equal to 45 degrees. The index of water is 4/3. That's n. N prime is the index of air equal to 1. Now we can plug into Snell's law to calculate alpha. N sine alpha is 4/3 sine alpha. N prime sine alpha prime is the sine of 45. The sine of 45 is 1 over 1.414. We multiply both sides by 3/4 to isolate the sine of alpha. And we get that alpha equals 32 degrees. Now we'll call the distance between the imaginary vertical line and the normal y. And we can figure out what y is from the tangent formula. Tan of 32 is y divided by 8. Tangent of 32 is 0.625, so y equals 5 feet. Now, the distance to the imaginary fish is x. This angle is 45 degrees. It's a vertical angle to the other 45-degree angle, so we can calculate x by tan 45 equals x over 5. Tan of 45 is 1, therefore x is 5 feet. So the fish is 5 feet, the apparent fish is 5 feet below the surface, or 3 feet above the actual fish. So a good rule of thumb when you're catching a fish is to aim lower. Question 6, what is the speed of light in glass? N equals 1.5. Now I said in Unit 5 that the index of refraction is related to how much a material slows down light. And here is the formula that you can use to calculate that. So the index of refraction of a material, in this case it's glass, that equals the speed of light in air divided by the speed of light in that material, in this case glass. So we're given that the index is 1.5, and we learned in Unit 1 that the speed of light in air is 3 times 10 to the 8th meters per second. So we can easily calculate the speed of light in glass now. And we find that it's equal to 2 times 10 to the 8th meters per second. Okay, we'll finish up with an easy question. What is the critical angle of diamond? N equals 2.5. So the formula is the sine of the critical angle equals the lower index divided by the higher index. So since diamond is surrounded by air, we have n equals 1 on the, n prime equals 1 on the top, 2.5 on the bottom is what n equals. And drum roll, we have the angle equals 23.6 degrees.